Hello everyone. In this video I will talk about another algorithm design paradigm known as the dynamic programming. The underpinning idea of the dynamic programming is this one, that is, an optimal solution must contain only optimal sub-solutions. If you are building up a solution for a larger problem, then all the constituent smaller problems of that larger problem should always be optimal. Then the dynamic programming is used where we have problems which can be divided into similar subproblems so that their result can be reused. Okay, so this is the main idea of dynamic programming. We'll be reusing the previous result that we have already obtained in order to build up the solution for the original problem. Now there is a subtle difference between dynamic programming and the divide and conquer algorithm. Unlike divide and conquer, these subproblems are not solved independently. Rather, the result of these smaller subproblems are remembered and used for similar or overlapping subproblems. In dynamic programming, we will never solve a subproblem more than once. The solution for the subproblem will be reused in the future. And another important property of dynamic programming is dynamic programming uses memorization. That we will be using certain memory in the computer in order to remember the previous calculation that we have already carried out in order to use it in the later stage of the algorithm. So these are the main properties of a dynamic programming algorithm, and we will work out the solution for a problem which uses the dynamic programming approach. The example that we are going to see is the ordering of matrix multiplication. Suppose you have four different matrices. Let's say the first matrix is A, and the dimension of A is 50 by 10, that is, we have 50 rows and 10 columns. And another matrix, let's say B, and which has a size 10 by 40, and another matrix C, and which has a size 40 by 30, and another matrix D, which has size 30 by 5. Now suppose that I want to find the product of these matrices A into B into C into D. So we know that the matrix multiplication is associative. That means that I can actually find the value of this product A, B, C, D by first finding the product of C into D. Then we can multiply that result with B. Then we can multiply the combined result of B, C, D with the value of A. And another way to do the same operation is first we can carry out the product of AB. Then we can carry out the product of CD. Then we multiply them together to get the final result of A into B into C into D. And the same result can also be obtained if I do it in this way, that is, first you take the matrix A, then you take the matrix B, multiply them first, then you take the matrix C, then you multiply them, then you take the matrix D and multiply D at the end. So this will be giving us the same result. And another way of doing the same multiplication is first multiply B with C, then you multiply the result with A, then you multiply the result with D. And similarly, one more possibility is there. First you multiply B and C, then you multiply this result with D, and finally multiply that result with A. Okay, so in total you have 5 different possibilities to find the product of the matrices A, B, C and D. This property is actually the result of the associative property of the matrix multiplication. So this indicates that we can parenthesize the matrix multiplication in whatever way we like, but the number of computations differ from one way to the other. So in this problem of ordering of matrix multiplication, our aim is to find a specific order of parentheses which minimize the total number of computations required to calculate the product of a given number of matrices. If we wish to know the number of ways in which a given number of matrices can be parenthesized for multiplication, then it is given by the equation T of n is equal to sigma I from 1 to n minus 1 T of I T of n minus I. So this is kind of a recursive relation. So as the base case we have T of 1, the number of possible ways to find a matrix itself is 1, and the number of possibilities by which we can parenthesize two different matrices is also 1, because if you have two matrices A and B, there is only one way to multiply these matrices, that is multiply A with B. Similarly, if you have three matrices, then you can have two different ways to multiply those matrices. That is, if you have matrices like A, B, C, you can either parenthesize it like this, or it can also be parenthesized like this. That is, first multiply A and B, then multiply that product with C. Otherwise, you first multiply B and C, then multiply the result of that with A. So there are two different ways by which we can multiply three different matrices. Similarly, if you want to find T of 4, then we can use this equation rather than listing down all the possibilities. That is, T of 4 will be sigma I from 1 to 3. That is, this one is n minus 1, where we have n equal to 4 here. So n minus 1 will be 3. T of I into T of n minus I. Okay. So this will be a summation of three different terms. So first one will be T of 1 into T of n minus 1 will be 4 minus 1, that is T of 3, plus T of 2 into T of n minus 2, that is 4 minus 2 is 2, plus T of 3 into T of 4 minus 3, that is T of 1. We know T of 1 is 1, so 1 into T of 3 is 2, so 2 plus T of 2 is 1 into again T of 2 is 1, plus T of 3 is 2 into T of 1 is 1. So this will be 2 plus 1 plus 2, that is equal to 5. And if we wish to find the number of ways by which we can parenthesize 5 different matrices, then it will be sigma I from 1 to 4 T of I into T of n minus I, and this will be T of 1 into T of 4 plus T of 2 into T of 3 plus T of 3 into T of 2 plus T of 4 into T of 1. We can have the value of I up to 4. So T of 1 is 1, T of 4 is 5, plus T of 2 is 1 and T of 3 is 2, plus T of 3 is again 2, T of 2 is 1, plus T of 4 is 5 and T of 1 is 1. So this will be 5 plus 2 plus 2 plus 5, so this will be 14. So there will be 14 different ways by which we can parenthesize a multiplication of 5 different matrices. Now suppose you have two matrices A and B. The dimension of A is P by Q, the dimension of B is Q by R, and if you are going to find the product A into B, then the total number of multiplications required to get the product of A and B will be P into Q into R. So as an example, if I have a matrix A equal to 2, 3, 1, 4, so this is a 2 by 2 matrix, and another matrix B equal to, let's say, 1, 2, 3, 4, 5, 6, so this is actually a 2 by 3 matrix. So the number of columns of A is equal to the number of rows of B, so we can have the multiplication of these two matrices. Now if you find the product AB, then you can find it in this way, that is 2 into 1 plus 3 into 4. This we are multiplying this row with this column. Similarly, the next element will be 2 into 2 plus 3 into 5, and the second row will be 1 into 1 plus 4 into 4, and the next element will be 1 into 2 plus 4 into 5, and the next element will be 1 into 3 plus 4 into 6. Okay, so this will be essentially a 2 by 3 matrix. So in this matrix we have total 2 into 3, that is 6 elements, and each of those elements takes 2 multiplications to calculate the final number. That means that what is the common dimension between A and B, that is the number of columns of A and the number of rows of B, then that much number of multiplications will be required to find a single element of the product. So if you have 2 into 3 elements in the product, then it will take 2 into 3 into 2 multiplications in total. So that means in order to find the product of AB, the total number of multiplications will be 2 into, that is this 2, then 2 into, that is this 2 into 3. So here we will have 12 multiplications, that is 2 for this one, 2 for this one, 2, 2, 2 and 2. So total we will have 12 multiplications. So if the dimension of first matrix is P by Q and the dimension of second matrix is Q by R, then the total number of multiplications required will be PQR. So this is an important point that we have to keep in mind while we discuss this example of dynamic programming. Now suppose that I have 4 different matrices A, B, C and D. The dimension of A is 50 by 10, the dimension of B is 10 by 40 and the dimension of C and D are given over here. So these are relatively bit larger matrices. Now we have to calculate the product A, B, C, D. Now the question is in which order we have to parenthesize these matrices in order to get the result with minimum number of calculations or minimum number of multiplications. So first I am examining the number of multiplications required to calculate the product A, B, C, D in this way. That is, first I am multiplying A, B, then I am multiplying C, D separately, then I am multiplying those two products together to get the final result A, B, C, D. So the number of multiplications required to find the product A, B will be, so this is the dimension of A, that is 50 by 10. The dimension of B is 10 by 40. So the total number of multiplications required to calculate AB will be 50 into 10 into 40. Okay, so that is written over here, 50 into 10 into 40. So this is the number of multiplications required to calculate AB. Okay, similarly the number of multiplications required to calculate CD will be, the number of rows of C is 40, the columns are 30. The number of rows of D is 30, the columns are 5. So the total number of multiplications required to calculate CD will be 40 into 30 into 5. Okay, so that is written over here. So this is the number of multiplications required to calculate CD. Now we have with us the product AB and we have with us the product CD. Now we have to calculate the multiplication of these two matrices. So the dimension of AB will be now 50 by 40. That is this one and this one, and the dimension of CD will be now 40 by 5. So this will be 40 by 5, and if you multiply these two matrices together, the number of calculations required will be 50 into 40 into 5. That is written over here, 50 into 40 into 5. So this is the number of multiplications required to calculate AB then CD. And if you do the numerical calculations, this will reduce down to 36,000 multiplications. Okay, and similarly if you take the multiplication in this way, that is, first you are multiplying CD, then you are finding B into CD, then you are finding A into B into CD. So the number of multiplications required for calculating CD will be this one, that is 40 into 30 into 5, that is 40 into 30 into 5. And the number of multiplications required to calculate B into CD will be this one, and similarly the number of multiplications required to calculate A into B into CD will be this one, and if you do the math you will get 10,500 multiplications. Similarly for the third case, first you are multiplying BC, then you are finding BC into D, then you are multiplying A with the result of these multiplications. So the total number of multiplications required to calculate BC will be this one. Then you will have to find BC into D. So the number of calculations required for that multiplication will be this one. Then finally you will be calculating A into BC into D. So this will be the number of multiplications required to calculate the final product. So in total it will be 16,000 multiplication. Similarly, if you take BC first, then multiply with A, then you multiply that entire product with D. So this will be the multiplications required to calculate BC, and this is for A into BC, and this is for A into BC into D. So this is the total number of multiplications. And similarly, the last case, we can have first multiply AB, then multiply that product with C, then multiply that product with D. The total number of multiplications for AB is 50 into 10 into 40. So this is for AB. Then for AB into C, this will be the total number of multiplications. And at the end, AB into C into D, this will be the total number of multiplications. If you calculate the numerical value, this will be 87,500. So you can see that the number of multiplications varies drastically when you change the order of parentheses. So the smallest one we have is this one, that is 10,500 multiplications, and the largest one is this one, that is 87,500 multiplications. So the order that we choose will definitely make the number of computations required for a computer. Now our aim is to come up with an algorithm where if you give the matrices along with the dimensions, it will be giving us the proper order so that the number of multiplications required to find the product of matrices will be as minimum as possible. Now suppose that a sequence of matrices is given as A1, A2, A3 up to AN. That is, we have to find the product of these matrices in this order. Now our aim is to find the parenthesis grouping in which the number of multiplications used to find this product will be as minimum as possible. And assume that the dimension of A1 is D0 by D1, and that of A2 is D1 by D2, and that of AN is Dn minus 1 by Dn. Okay, which means that the number of rows of A1 is D0 and the number of column is D1, and the number of rows of A2 is D1, the number of columns is D2. That means that the matrix index as well as the column index is the same, and the row index will be 1 less than the column index. Alright, so this is the notational convention that we are following. M of ij represents the minimum number of multiplications required to calculate the product ai through aj, which means that m of 2, 3 will be the minimum number of computations required to calculate a2 into a3. Similarly, m1, 4 will be the minimum number of computations required to calculate a1, a2, a3 and a4. Okay, so that is the meaning of this notation mij. Another point is mi comma I will be always 0, because if you want to find a matrix A1 from a multiplication, that doesn't make any sense, because you do not need to carry out any number of multiplications. So the number of multiplications required to find a matrix itself is 0. Okay, since no product is required. Now the optimal solution of ai through aj must break at some point k where I less than or equal to k less than j. This means that, let me clear this off. This means that if you want to find the product of a1 into a2 into a3 into a4, then this sequence should break at some point k. That is, you can have a1 separately, then you can have a break, then you find the product a2, a3, a4 separately. Then in that case k will be 1, that is, you are breaking at this point. Similarly, you can also break at the second matrix, then the product will be in this form, that is a1, a2, a3, a4. Here the value of k is 2. Similarly, you can break at 3, that is a1, a2, a3. Then you multiply a4 separately, so you are breaking at this point. Okay. Now you cannot break at 4, because if you break at 4, you are essentially calculating the same product that is required to calculate. Then if you are breaking at some point k, the number of multiplications required will be mij is equal to mik plus mk plus 1j plus di minus 1 into dk into dj. That means that, let me take this example. Okay, so if you are calculating a1, a2 into a3, a4, then in that case the number of multiplications required will be equal to the number of multiplications required to calculate this product, then the number of multiplications required to calculate this product, plus the number of multiplications required to calculate these two matrices together. So the number of multiplications required to calculate a1, a2 will be m1, 2. The number of multiplications required to calculate a2, a4 will be m3, 4. Then the number of multiplications required to calculate the product of these two matrices will be d0, d2 and d4, because the number of rows of a1 will be d0, that is if the matrix index is 1, then the number of rows will be 1 less than the matrix index, that is D0. Then the number of columns of that product will be D4, that is the last matrix column index, that is D4. Then you have to find the number of columns of A1 into A2. The number of columns of A1 into A2 will be equal to the number of columns of A2, that is D2, and it will be same as the number of rows of A3, that will be also D2. So this is the calculation required to find the product of these two matrices. Okay, so that is actually this equation indicating if I want to calculate the product from A1, A2, A3, A4, and you are breaking at some k, here the value of k is 2, then the total number of computations will be M12 plus M34. Then in this case it is actually calculating M14 is equal to M12 plus M34 plus this is equivalent to this one, that is D0 into D2 into D4. As the final equation, if you want to find the minimum number of computations, then Mij will be equal to 0 if the index of I and j are the same, that is you are finding a matrix from itself, then no multiplication is required, so you can write it as 0. And similarly, if the value of I is less than j, which indicates these cases, then the minimum number of computation can be found by varying the value of k from I to j. Then the minimum number of computations can be found by using this equation, where you are varying the value of k from I to less than j. Then you are calculating all the possibilities of this equation, then you pick the minimum one. That is the possibilities in this particular case. If you have to calculate M14, you can have the value of k at this point, at this point, at this point. You can have the value of k at equal to 1 or k equal to 2 or k equal to 3. Then you pick the combination which gives the minimum value for this equation. Now let's look at one example where we will work out these processes. Now imagine that I have 5 different matrices A1, A2 up to A5. I need to find the product A1 into A2 into A3 into A4 into A5. Now if you look at these dimensions, A1 has got a dimension 2 by 3. So the value of D0 will be 2, D1 will be 3. Similarly, A2 has got a dimension 3 by 5. So D1 is 3. The value of D1 can be taken either from here or here because both of them should be the same. Otherwise the multiplication of A1, A2 will not be possible. I can list the values of D's in a table like this one: D0, D1, D2, D3, D4 and D5. D0 has a value 2, D1 is 3, D2 is 5, D3 is 2, D4 is 4 and D5 is 3. Okay, we will make use of these values later in our calculations. Now as the first step, we can definitely write M1, 1 equal to, that is the number of multiplications required to find the matrix A1 is M1, 1 which will be 0, which is same as M2, 2, which is same as M3, 3 equal to M4, 4 equal to M5, 5, and this will be equal to 0. Okay, I'm utilizing a table here where we will be recording all the values of M. So I will be writing M, so M11 is 0, M22 is 0, M33 is 0, M44 is 0 and M55 is 0. Okay, that is the number of multiplications required to calculate the product from 1 to 1. And if I write something over here, that will be the minimum number of multiplications required to calculate A1 into A2. If I write something over here, that will be the minimum number of multiplications required to calculate the product from A1 to A4. And our task is to find the value at this position. That will be the minimum number of multiplications required to calculate the product from A1, A2, A3 up to A5. Next, we will calculate the number of multiplications required to calculate the product of every pair of matrices. So first we will calculate the number of multiplications required to calculate the product A1, A2, then A2, A3, then A3, A4, then A4, A5. So the number of multiplications required to calculate A1 into A2 will be M12. That will be minimum of k from 1 to 2 minus 1, that is 1, 1 to 1. Then I have to calculate M of 1 comma k plus M of k plus 1 comma 2 plus d0 d1 d2. So as we have only one value for k, then that will be a single equation. So I will be writing m1 comma 1 plus m2 comma 2 plus d0 d1 d2. So we know that m1 comma 1 is 0, m2 comma 2 is 0. These three will be the product of these three numbers, so that will be 30. So 30. So the number of multiplications required to calculate a1 a2 will be 30. Similarly, m2 comma 3 will be d1 d2 d3. d1 d2 d3 will be 3 into 5 into 2, which is equal to 30 again. Then next we have to calculate the minimum number of multiplications for multiplying a3 and a4. So that will be d2 d3 d4, that is equal to 5 into 2 into 4, which will be 40. So that is equal to 40. Similarly, m4 comma 5 is equal to d3 d4 d5. d3 d4 d5 is 2 into 4 into 3, that will be 24. Okay, so I'm going to write those values here. m1 comma 2 is 30, m2 comma 3 is again 30, m3 comma 4 is 40, and m4 comma 5 is 24. Okay, later in our calculation we will be utilizing these values. This is the point where we are using the memorization technique. Okay, so we will be utilizing the same result for future calculation. Now we will consider the combination of three different matrices. That is, we have to find a1 a2 a3 a4 and a5. So first we will take a1 to a3, then a2 to a4, then a3 to a5. Okay, so we have the equation m of I comma j equal to minimum of k from I to j minus 1, m of I comma k plus m of k plus 1 comma j plus di minus 1 dk and dj. Okay, so when you calculate the product a1 to a3, then it will be m of 1 comma 3. So we will be calculating minimum of k from 1 to 2, m of 1 comma k plus m of k plus 1 comma 3 plus d0 dk and d3. So this will be equal to, so we have two cases for k can be equal to 1 or it can be equal to 2. So we will be picking the minimum of m of 1 comma 1 plus m of 2 comma 3 plus d0 d1 d3, or if you substitute k equal to 2, this will be m of 1 comma 2 plus m of 3 comma 3 plus d0 d2 d3. Okay, now we will choose minimum of m of 1 comma 1 is 0 plus m of 2 comma 3, m of 2 comma 3 is 30 plus d0 d1 d3. d0 is 2, d1 is 3 and d3 is 2. So we will have 6 into 2, that is 12, comma m of 1 comma 2, m of 1 comma 2 is 30 plus m of 3 comma 3 is 0 plus d0 d2 d3. So D0, D2 and D3. So D0 into D2 is 10, into D3 will be 20. Okay, so this will be 20. So we have to calculate minimum from 30 plus 12 is 42 and 30 plus 20 is 50. So the minimum is 42. So this is when the value of k is equal to 1. The meaning of k equal to 1 is if you want to find the product of a1, a2, a3, then you have to break it k equal to 1. That is, you have to find the product by taking a1 separately, then a2 and a3 as the next component, rather than taking a1, a2, then multiplying it with a3, because this will result in a total multiplication equal to 50 and this will result in total multiplication equal to 42. Similarly, you can calculate the value for M24. The value of M24 will be 54. You can also calculate M35. M35 is again 54. Okay, this is when you take the value of k equal to 3, and this is also when you take the value of k equal to 3, which means that a2, a3 into a4 will be using lesser number of computations than a2 into a3, a4. Okay, and similarly when you write k equal to 3, this will be a3 is taken separately, then multiply that with the product of a4 into a5. Okay, that is the meaning of k equal to 3 in this case. So we have the value of M24 and M35 equal to 54 and M13 is 42. Okay, so I will write those values here. M13 is 42, M24 is 54, and again M35 is 54. Now we have to calculate these three values also. In A1, A2, A3, A4, A5, you can take combination of 4 different matrices. So the first combination is the product from A1 through A4 or the product from A2 through A5. First I'm writing the equation for M14. So M14 will be minimum of k from 1 to 3, m of 1 comma k plus m of k plus 1 comma 4 plus d0, dk and dj. Let's examine each of those cases. So this will be minimum of, then when k equal to 1, this equation will be m of 1 comma 1 plus m of 2 comma 4 plus d0, d1, d4, or when k equal to 2, this equation will be m of 1 comma 2 plus m of 3 comma 4 plus d0, d2, d4, and the last case will be when k equal to 3, so that will be m of 1 comma 3 plus m of 4 comma 4 plus d0, d3, d4. Okay, and I fill up those values. M11 is 0 plus M24 is 54 plus d0, d1, d4. d0, d1, d4 is 2 into 3 into 4. Then M12 is 30 and M34 is 40 plus d0, d2, d4. d0, d2, d4 is 2 into 5 into 4, and for this equation M13 is 42 plus M44 is 0 and d0, d3, d4 is 2 into 2 into 4. Okay, so we have to pick the minimum value out of it. So minimum of 78, 110, 58. So this will be 58. That is when k equal to 3. Okay, similarly you can find m of 2 comma 5. That is our next combination, m of 2 comma 5. If you do the computation, you will get it as 72. That is also when k equal to 3. So we can fill up this table, that is we have 2 5 as 72 and 1 4 as 58. So 1 4 is 58 and 2 5 as 72. Okay, now we have only this cell left. So let me bring this table down. Now in the product A1, A2, A3, A4, A5, we have only this combination to examine, that is the multiplication from A1 through A5. We are calculating m of 1 comma 5. So the equation will be minimum of k from 1 to 4, m of 1 comma k plus m of k plus 1 comma 5 plus d0 dk d5. Okay, so this is equal to minimum of, we will have 4 different possibilities, that is m of 1 comma 1 plus m of 2 comma 5 plus d0 d1 d5 comma m of 1 comma 2 plus m of 3 comma 5 plus d0 d2 d5 comma m of 1 comma 3 plus m of 4 comma 5 plus d0 d3 d5 comma m of 1 comma 4 plus m of 5 comma 5 plus d0 d4 d5. Okay, when you write those values, it will be minimum of m11 is 0 plus m25 is 72 plus d0 d1 d5 is 2 into 3 into 3, then m12 is 30 plus m35 is 54 plus d0 d2 d5 is 2 into 5 into 3, then m13 is 42 plus m45 is 24, then d0 d3 d5 is 2 2 3, then the last option is m14 is 58 plus m55 is 0, then d0 d4 d5 is 2 into 4 into 3. Okay, so this will be the minimum of 90, 114, 78 and 82. Okay, so the minimum of this one is 78. This is when k is equal to 3. Okay, so I can fill up the table with the last value, which is 78. Okay, so here the value of k equal to 3 means if you want to find the product of a1, a2, a3, a4, a5, you have to break at 3. Okay, that means that if you want to find the product of a1 through a5, you have to find the value of a1, a2, a3 first, then you have to find the product of a4, a5, then multiply them together. There is no different ways of calculating a4, a5, but you can examine the way of calculating a1 to a3. So if you find the value of m13, so we have the value of m13 is 42. In that time you had to break at k equal to 1. So that means that you had to break at this point. That is the meaning of k equal to 1. Essentially, if you want to calculate a1 into a2 into a3, then you had to break at a1. So that means that you had to take a1 separately, then you multiply with the product of a2, a3, then you multiply that product with a4 and a5. Okay, so this is the best way of multiplying these 5 matrices so that the number of multiplications can be made equal to 78. Okay, and if you take any other order, the number of multiplications will be more than 78. In this case of finding the product from A1 to A5, we are examining all the sub-problems, and out of those sub-problems we are taking the optimal one. That is the meaning of dynamic programming. An optimal solution should contain optimal sub-solutions. Okay, so I hope it is clear. Thank you.